Okay, so hello everybody. Hope you had a good weekend, and I hope, as always, what I say is I hope you got a little time to go through whatever we have done so that we can build up on that in the next lectures. Okay, so uh, just a quick recap. What we did in the last class was the solid solution, which we also call the non-stoichiometric defects or the extrinsic defect. Extrinsic defect, why? Because we deliberately introduce those defects. And intrinsic defects are those which are present in the material by virtue of the thermodynamic stability, the lowering of free energy. Okay. And then we read about why should we study solid solution at all, various applications of or various advantages of studying solid solutions. Then types of simple solid solution and numero 3 rules. That is, two members will form a solid solution if they have similar size, similar charge, and isostructure. However, all these are not very necessary, and a little bit here and there work, but then we fall into the regime of complex solid solution. Okay, then we read about substitutional and interstitial solid solutions. Complex solid solution, we also did some examples wherein we studied what will happen if host and guest ions, they have different charges. And we studied a particular case where the charge on the guest would be greater than charge on host. In that case, we are expected to get uh, cation deficient solid solution and anion excess solid solution. And we also did an example. I hope you tried to work it. And important thing is that mechanism of solid solution, whether it is cation excess, anion deficient, or vice versa, that cannot be predicted. That has to be determined experimentally. Okay. Then we came to the next case. What will happen if your cation or your the guest ion has got the lesser charge than the charge on the host ion. And therein we did the example of substituting calcium in place of zirconium in ZrO2. And we realized that because calcium has got the smaller charge, lesser charge, when it substitutes Zr4 plus, so to compensate for that lesser charge, either we should have cation vacancies or we should have I'm sorry, either we should have cation excess because we need to increase the positive charge in the material, or we should have anion vacancies. And in both the cases, how to write the nominal formula, that also we did. And then we also read a very important technological material, which is anion deficient zirconia, also called the stabilized zirconia, which has applications as superior oxide ion conductors. And why does it behave as an oxide ion conductors? Two reasons. One is it has got vacancies, oxide ion vacancies, which helps in the movement of hopping of oxide ion from one place to another, thus leading to the conductivity. And second, when we substitute calcium in place of zirconium or yttrium in place of zirconium, what happens is your lattice expands and it goes from ZrO2, otherwise is monoclinic, it becomes cubic. And the cubic fluorite lattice is very, very conducive to anion conduction. In fact, some of the so-called super ionic conductor, for example, lead fluoride and all, they have got fluorite lattice. Okay. Why? Because fluorite lattice has got a lot of free space for the ions to move. Just remember these little points. Later on, these help whenever you design your experiment or give your answers in some question or think about some other logic related to that. Okay. Then we also studied about what is double substitution. Uh, Substitution can happen both at cation and anion side. Okay. I think charge on guest. Okay, we have done this. Okay, I think one more example I should be giving you here. Here, the charge on the guest is less than the charge on the host. Okay. And what did we do? We compensated it by creating, okay, let me put the laser pointer on. We compensated it by creating the oxide ion vacancies. There is one more way which we have shown here that you can get the cation excess also. Okay. Uh, yeah, I think this formula is wrong, but I'll give you a better example. Now, cation excess, all of you have heard of aluminosilicates. Okay. You have silica Si4 plus ion, which is replaced by Al3 plus ion. Now, when the higher charge ion is replaced by the smaller charge ion, again the same situation, the positive charge in the material decreases. So, you have to either increase the positive charge or decrease the negative charge. We have already talked about decreasing the negative charge. In aluminosilicate, it is the other thing that is followed, that is cation excess. And how does that happen? You replace Si4 plus by Al3 plus, and the excess positive, the extra positive charge that you need in the lattice is compensated by alkali ion, Na plus or Li plus or K plus, moving in the channels of the aluminosilicate. I'm sure all of you would have heard about famous aluminosilicates like lithium aluminosilicate and other such species, which are actually charge compensated aluminosilicate, where charge is compensated by the lithium ion or sodium ion. So this is how solid solution, you probably would have read it earlier or you read it with me here, but knowingly or unknowingly, you've been encountering solid solutions in your day-to-day life. The most important one of which is we've talked about in the previous class is the steel. All of us use steel utensils at home and they are nothing but interstitial solid solutions. Okay. So double solution substitution we've already read about in the last class. Okay. Now, what are the techniques employed to study solid solution? What I gave you I gave you two compounds or two materials or three materials or four materials, and I asked you to mix them. You mix them, heated them at high temperature or by whatever method, high temperature or the low temperature synthesis. You obtain something, and you want to now study whether you have got solid solution or not, or if you have got the solid solution, how to quantify it. Okay. The first and foremost, as a solid state chemist, as a solid state physicist, as a material scientist, the technique, the bread and butter technique is X-ray diffraction. Why? Because it tells you about the structure. It shows whether the solid solution has formed or not. And once you know the solid solution has formed, you can determine the cell parameter of the solid solution from X-ray patterns. Okay, I'll just describe this a little later also. Those of you who have already done solid state, who have done PhD or are doing PhD, probably for you this point might be a little trivial, but it's good for the people who really have not done a lot of experiments. Density measurement. Solid solution formation affect the density. I mean, even if I don't tell you this, this is a very, very common sense thing. If I'm creating vacancies in the material, ideally, if nothing else happens, it should lead to the decrease in the density of the material. And if the interstitials are going, or in other way, if the anion excess or the cation excess solid solutions are forming, that should lead to the increase in density, given everything else is same. So solid solution formation affect the density, and hence we can measure the density of the material that we have obtained, and that will also tell us about the solid solution formation and even the mechanism of solid solution formation. Okay. There are various other changes in property. See, you are introducing something in a material, right? So it is bound to affect the properties, whether you want it or not. Sometimes it happens because you wanted it to happen. That is why you made solid solution. Sometimes it happens because it could be impurities and you didn't want them, but you should know them, right? That they have happened to your material. So other techniques other than X-ray diffraction and density measurement, which are the most common techniques. Of course, when I say X-ray diffraction, that means other diffraction techniques also. You can have neutron diffraction and electron also. However, this one is the easiest one to carry out. Okay. So other properties are thermal analysis techniques such as DTA and DSC. When you form solid solution, and because the solid solution is also a crystalline phase, okay, so that will affect, and your composition is changing. Your composition is changing means that is changing your average bond strength. And we read about it earlier. The bond strength is directly related to the lattice energy, which is directly related to the melting point. So solid solution formation affects the melting point of the material as well. Okay. For example, if you have iron, its melting point is 910, close to alpha iron. It is close to 910. But if you substitute very small amount of carbon in it, it shows a stark decrease to 723, which can be easily measurable. So this is also one of the technique by which you can study your solid solutions. Okay. Now there is something called Vegard's law. What is Vegard's law? It is good to know this. Okay. So Vegard's law states that the lattice parameter of the solid solution formed between two solids A and B is the linear function of composition. In very simple terms, what does it mean is, if you have A and its lattice parameter is 5, and if you have B and its lattice parameter is 10, assuming they are forming the complete solid solution, the lattice parameter of the solid solution, say A 0.5, B 0.5, should be the average of A and B. Okay, which now I'll repeat again the Vegard's law. The lattice parameter of the solid solution is the linear function of the composition. Okay, what it says is that it should linearly vary from A to B. But most of the time, in fact, many a times, Vegard's law, it is generally followed, but it is followed in those cases which we read in case of Hume-Rowe 3 rules, no? Comparable sizes, similar charges, and then your isostructural, if those kind of conditions are there. In fact, I've myself worked on some system which are completely soluble in each other in whatever proportion you mix it in. And their lattice parameter is, they also vary linearly. You have A, you put 10 of B, it comes here. You put 20 of B, it comes here. But most of the time, because our solid solutions are, they do not follow all those rules, no, or your end members, that they're isostructural and similar charges. So, Vegard's law fails. Most of the time it is not possible. In fact, observing 100% solubility itself is very difficult. But even if it does, Vegard's law assumes that your host and guest atoms, they are hard spheres. And that is why whatever resultant lattice parameter you would achieve by their mixing up would depend only and only on the sizes of the host and guest ion. Okay. Now that is very easy to believe, easy to imagine also. I have a bigger ball, I have a smaller ball, some number of bigger balls, some number of smaller ball. Now, when I mix them up, I arrange 10 big balls and I arrange 10 small balls. If I arrange 5 big balls and 5 small balls, obviously whatever length dimension that you will get would be average of what you would have achieved by arranging the bigger balls and the smaller balls, right? And this is what Vegard's law assumes. It assumes that your host and guest atoms are hard spheres. But in real system, that's not possible, okay? That doesn't happen. Your atoms and ions are not completely hard spheres. So if what happens is, if your AA, that is the AA and BB interaction, that is the interaction between the end member themselves, if they are very strong as compared to AB interaction, then you observe a positive deviation from Vegard's law. Why? because they're happy with their own kin. A is happy with A and B is happy with B. So even if you mix them, if I'm able to pinpoint each A and each B in my material, what I will, which XRD cannot do, what I will see is that A likes to be with A and B likes to be with B. Even though overall, I'm seeing that they have mixed up. So what it leads to? It leads to some kind of positive deviation. You observe the lattice point at this, lattice parameter this, but it comes here. Okay. But however, if the interaction between A and B, that is the end member, it is much more as compared to what they had with their own kin, with their own similar kind of atom, then you observe negative deviation, because now they bond strongly when they mix up. So when they bond strongly when they mix up, you observe the negative deviation from what was anticipated only based on their sizes. Okay. So I hope it is clear. Let's just try to see. Okay, this is one system that I myself did. Very well reported system for the people who work in nuclear material. YSZ is aqueous stabilized zirconia, which we just read about a few slides back. Just for your purpose, just assume that it is a fluoride type phase, and thoria is also fluoride type phase. Similarly, ceria is fluoride, and YSZ, as I said, is fluoride. Okay. So what we did is we mixed up thoria and YSZ. See, both of them are isostructural. Similarly, here also both of them are isostructural. But what is happening is I've only shown here the XRD pattern of the end members, ceria, YSZ, thoria, YSZ, and just one solid solution, 50-50 between them. And I'll show you how we study the XRD pattern. You record the XRD pattern of one end member, YSZ. You record the XRD pattern of other end member. And then you start recording the XRD patterns of the Beechka compositions. As you can see here, the XRD pattern of this solid solution is similar to the end members. That means it has also adopted a fluoride type structure, and it is a solid solution. I cannot see any set of peaks which correspond to YSZ or any set of peaks which correspond to ceria. I observe only one set of peaks which, by my experience, and those of you who do XRD know, belongs to F-type phase. So what XRD tells me, you have observed a single phase which takes up the fluoride type structure. If I wish I had modified it, but if you look at it closely, you can see that there is a shift in the XRD peak towards lower 2 theta value, lower angle. This x-axis is your angle. I'm not supposed to teach you details of XRD, which the other lecturer would do, but this also shows that there is a miscibility. Cerium 4 plus is bigger than YSZ, and your lattice parameter and 2 theta are inversely related. Okay. So if I will plot, which I will show you in the next slide, I will observe a shift in the lattice parameter. However, the same thing when I look at this system, thoria gave me fluoride type, YSZ gave me fluoride type, but the intermediate composition showed me one set of peaks which are marked as stars, which are YSZ-like, and one set of peak which is thoria-like. That means these two have not mixed up. Now see, even though both of them are fluoride, this is here, this is because the size of thorium 4 plus is much bigger than the size of average cation in YSZ. So they don't mix up. They don't really mix up with each other because the sizes are too different. Okay. So that is how we study. So here the XRD pattern will tell me, my XRD doesn't know that I had end member as thoria or YSZ. It simply tells me that you have two phases here which are both of fluoride type. And when I compare this pattern with my end member, I have the entire story clear in front of me. Okay. This is how XRD studies help in studying your solid solutions. This is one example of Vegard's law, one system which shows the complete linear dependence on composition. This is 0% ceria, and here it is 100% ceria. So obviously 100 minus the other value is the amount of YZ. Now Syria 100% has bigger size as compared to YZ. YZ 100 is here. So as I increase the amount of Syria I must say, the lattice parameter increases in a very, very systematic way. And this is one of the system that follows Vegar's law. Okay. So, and this is an example of density measurement. Okay. Now, here we have two solid solution, calcium oxide in ZrO2 and calcium fluoride in YF3. So what we do in density measurement, we determine the theoretical density. Okay. Now these dots are the, these are the assuming now calcium oxide, if I put in ZrO2, we discussed some time back, I have two options. I can get anion deficient, I can get cation excess. So what I do is I determine the theoretical density, assuming I will get cation excess and assuming I will get anion vacancies. And then I experimentally determine the value of densities. Then wherever they match with, whichever curve they match with, will tell me what is the mechanism of solid solution formation. So here, as we can see, and we know also that in ZrO2, the solid solution formation mechanism is anion vacancies, whereas in CF2 and YF3, the now what we have is the interstitial anion, that is anion excess that is happening here. Okay. So these were the methods by which we can determine, we can study our solid solution. So that brings us to end of the non-stoichiometric defect, which we also call solid solution. We studied about the type of solid solutions, which was simple, substitutional, interstitial, and also what happens when we have aliovalent. Reminding you what aliovalent means, when your two mixing ions, they have different valencies, different oxidation state, different charge. And then we also studied how to study the solid solution once we have formed it. Okay, taking a minute's break here, and then we come to the next topic, which is the phase transitions. Meanwhile, if you have any doubt, you're free to ask it. Okay, and one of your assignments, either it has been uploaded or would be uploaded today. So just have a look at it. And if there is any doubt, you can always write to me or we can discuss it in the next class as well. Okay. So all of you know what is a phase transition? In some way or the other, all of us have encountered it. When we boil water, it goes from liquid to vapor. That is nothing but phase transition, right? But here, what we are talking about is phase transition in solids. Okay, so what is a phase transition? If I have to define it, what I would say is change of one crystalline form of the material to another in response to some external stimulus, which could be the change in temperature and or pressure. The change in both temperature and pressure, the change in temperature or the change in pressure. Okay. So change of one crystalline form of material to other crystalline form of material in response to the change in temperature or pressure is called phase transition. Sometimes, however, what happens is like we were talking about the solid solutions. Sometimes as you change the composition of the material, then also you observe the phase change. In fact, we did one example. No? We said ZrO2 is monoclinic. And as I substitute calcium or yttrium in place of it, it becomes cubic fluoride. So that is nothing but a phase transition. However, here the phase change was happening in response to composition. And that is also actually a phase transition. But many a times change in phase as response to composition is not considered in the category of phase transitions when we are studying them. Otherwise, that is also as good a phase transition. Okay. So what are polymorphs? We just said that change of one crystalline form to another is a phase transition. So those two crystalline form which were getting converted from one another, they are called polymorphs. So two or more different crystalline form of the same material. The composition is same, but they are different crystal structure. For example, silica has got many crystalline form. One is quartz. All of you have seen quartz glassware. Then cristobalite, tridymite, stishovite is a metastable form of silica. It is formed at a high pressure. Then barium titanate, we read about it. We said tetragonal barium titanate is ferroelectric. And when you increase the temperature, it loses ferroelectricity because it becomes cubic. So cubic and tetragonal are the two polymorphs of barium titanate. Okay. So how do we classify phase transition? See, it is why now, actually, when I also used to study it, there's one thing which I would always wonder right from school days. Why the hell do we need classifications? Why do we have to memorize classification? See, why do we talk about classifications at all is later on, suppose anybody or for that matter, you are working in some material and you observe a phase transformation which is not reported earlier. That happens with the scientists, okay? And you are seeing certain characteristic which is belonging to a particular class of phase transitions already happening. But that phase transition, you are only out of 10 characteristics, say, you are able to study only 3, and those 3 are matching with a particular set. So then it makes a lot of logic to study rest of the 7 properties also and see whether your phase transition follows that as well. So once you are able to classify your material, your phase transition or whatever, then it helps you to know what direction you should proceed in. So this is how I understood that people do classification, and this is why the classifications are reported. So phase transformation are basically classified into on 2 characteristics, and they can be overlap also. One, mechanism, how the phase transition is actually happening. The mechanism of it. On the basis of it, it is classified as reconstructive or displacive, and on the basis of its thermodynamic behavior. We'll study about both the classifications now. Okay, so reconstructive phase transition. As the name suggests, reconstructive means breaking, forming. Simple thing. You are reconstructing something. So transition occurs by breaking and appropriate rejoining of the bonds in the new phase. Now what happens is, all of you know that bond breaking requires energy. That means anything, the phase transition here, they need energy, and because they need energy, there's a very high probability that the reconstructive phase transitions would be slower. Okay, they would need high activation energy because bond breaking and bond formation are needed. Also, because you are breaking everything and then reassembling. So there is a high chance that there is no symmetry relationship between two of your polymorphs. Okay. So for example, just pardon this error, graphite to diamond. Now graphite is your stable form of carbon at room temperature. All of you know that. However, when you increase the temperature and pressure, graphite converts to diamond. Okay. Now this is a phase transition happening between two phases of carbon. But if you look at it, graphite has got sp3 carbon. Okay. So there are graphite has got sp2 carbon and it has got layered structure like this. Whereas your diamond has got sp3 carbon where each carbon is attached to or 4 more carbons. So it is a 3-dimensional network, while this is a layered structure. So obviously there is no symmetry relationship between them. And obviously if you want to go from this to this, you would need to break the bonds and form the bonds. Okay, that is why the graphite to diamond phase transition requires very high pressure and very high temperatures. Okay, it is one of the typical example of how the reconstructive phase transitions are. Similarly, silica has got 3 polymorphs, quartz, which converts to cristobalite, and that converts to tridymite. Now, silica, all of us know, has the basic unit is SiO2 in whatever polymorph you see. It is SiO2 only, unlike the carbon polymorphs. But the way those SiO4 tetrahedra are linked together, whether they are chains, they are heats, they are linear chains, or they are three-dimensionally this thing. So the way those tetrahedra are linked, that differentiates these polymorphs. Okay. The second one is, the first one was reconstructive phase transition. Now, second is displacive phase transition. Again, this class is going to be very simple. Displacive, again, simple English. What does displacive means? Here, the bonds are not broken. The atoms are simply displaced with respect to one another by smaller distances, and that distance could be equal to the internuclear distance, or it could be even smaller than that. Now, because it is only movement of bonds, what happens is they are fast. Very small atomic movement, and the time required to complete the motion is of the order of lattice vibration, which is very small. Now, because it is fast, obviously, it will have low or zero activation energy. And also, it is only happening by twisting of bonds and all. There is a definite symmetry relationship between the two polymorphs that are linked by displacive phase transition. Okay. For example, we just read about silica. Silica goes from quartz to tridymite to cristobalite, and these are reconstructive. I told you in previous slide. Each silica has got an alpha and beta form, and they are formed just by tilting of SiO4 tetrahedra. So these transitions, A, B, and C, they are displacive phase transition. These transitions are reconstructive phase transitions. Okay, just showing you pictorially a very simple thing. Suppose you have this kind of linkages. Just imagine some arbitrary linkage. If you want to convert from this to this, or this to this, or this to this, you need to break some bonds and form some bond. So if you go from this to either any of these, that would be the reconstructive phase transition. However, if you want to convert this to this or this to this or vice versa or any of these three, that would be displacive phase transition. So I hope that is very clear to you now. Okay, so before I come to this example, let me see in chat that this class is very clear till now. Because I have been speaking continuously and I have not had even a single doubt. Okay. So I guess we are going fine till now. Repeat the last example. Okay. Last example is that is not even an example. I thought this should be pretty clear. Suppose you have linkages like this and you want to change this into any of these three. It is very much obvious that you will have to break some bonds and form some bonds. So transition from this to any of these is the reconstructive phase transition. You are breaking and reconstructing. But if you want to convert B to C or B to D or C to D and C to B or whichever way among these three, you just have to tilt these squares. Okay. And that is why the transition among these three is the displacive phase transition. All right. Now, I'll take you to a very interesting displacive phase transition, which is very common one also. This thing. This is rock salt to cesium chloride phase transition. How does it happen? Now, before I discuss this, I want all of you to take a minute and remember what is rock salt structure. Ideally, you should not have forgotten it because we have like repeated rock salt structure probably in every class. Okay, but still rock salt, all of you know, NaCl, which means Na at all the corners, face centers, Cl at the body center and edge centers. And your CaCl is the simple primitive lattice where you have Cl at the center and cesium at the corner, or you can take vice versa also. Here I'm taking Cl at the center because I want to compare it with this. Now, your rock salt structure, materials with rock salt structure, at high pressure or at low temperature, they go to cesium chloride structure. And that is a displacive phase transition. And how would that be? Let us see how does that happen. Okay. Just look at this tube. I have, so at corners, we have Na. I won't say Na or cesium here, or let me say Na, because, you know, that would make the things clear. The dots are Na, and of course, there is a dot here also, here also, here also, here, and here. Just that I am only drawing the dots which I need to make you understand this phase transition, okay? But you must understand that these dots are sodium and they are present at all the corners and face centers. And your chlorine are present at all the edge centers and the body center, okay? Now you concentrate only these sodium, this corner, okay? And these face center ones, all the 6 face center ones, okay? Now what happens is, this is your body diagonal, huh? 1, 8 is your body diagonal. Now you hold this body diagonal, this is your 1 and this is your 8, and squeeze it, okay? And now you try to imagine, once you squeeze it, you have something like a cube. जिसका top face is 7, 8, 3, 4. 7, 8, 3, 4. Okay. And the bottom face is 5, 6, 2, 1. 5, 6, 2, 1. And these two faces, right now it is across the body diagonal, they'll come closer to each other and they'll form something like a cube. And this cube, whatever you have formed by squeezing or shrinking this body diagonal, will have chlorine at the center. So once you have this kind of a structure wherein you have NAs at the corners and chlorine at the center, what you have obtained is the primitive cesium chloride type of lattice. Okay. So here the coordination number of chlorine was 6. What was that 6? 6 sodium at all the face center, because it was at the body center. This, and this. But here the coordination number of the chlorine becomes 8. Okay. So this is called rock salt to CaCl phase transition, and it is a displacive phase transition. Is that clear? Tell me if that is clear. How is this transition happening? Okay. Nice. Okay. Now there is one more classification, which is not really, wait, let me go to the previous slides. 1 and 8. 1 and 8 are not the nearest neighbor, okay? They are at the body diagonal of the new cube. In fact, they were at the body diagonal of the old cube as well. But now they are forming the body diagonal of the new cube, but they are not coordinating among to each other. They are not the nearest neighbors of each other. Okay. Now there's another classification, which basically is based on your reconstructive and displacive. That is why I don't teach it separately. But since it is mentioned in AR West, and which, as I told you, is I follow that book, so I thought it is good if you know that. So transition can also be classified by in what coordination sphere they are happening around the central atom. Okay. For example, you concentrate on one atom as your central atom, and the mechanism of the phase transition, according to that mechanism, the changes are happening in what coordination sphere, whether it is a first coordination sphere or the second. On the basis of that, the phase transitions are classified. For example, the transitions involving first coordination, they can also again be of reconstruct. They're happening in first coordination, remember that. And now they can be reconstructive or dilational. Reconstructive, the example we know, diamond and graphite, because one, when you have to convert from sp2 of graphite to sp3 of carbon, you're working in the first coordination only of the center carbon. In diamond, this is the center carbon is attached to 4. In graphite, it is to 3 and forming layered structure. So diamond to graphite is the first coordination sphere, reconstructive phase transition. However, we just read about rock salt cesium chloride. That is also in the first coordination sphere, but that is dilation. Transition involving second coordination sphere. As I told you, in various polymorphs of silica, SiO4 unit is intact. So first coordination of dilational is displacive. Dilational, that expands or contracts. Okay. So this in silica, your basic SiO4 unit in all the silica structures, that is intact. Okay. Nothing happens to silicon oxygen bond. So in all the silica related phase transitions, you're always working in the second coordination. So there you can have reconstructive when quartz goes to cristobalite and then to tridymite. Displacive, quartz goes to low and high quartz, cristobalite goes to low and high quartz, tridymite goes to low and high tridymite. So that is only tilting of SiO for polyhedra. Okay. Then I think this I have not taught you about order disorder, which we'll do later. So maybe we can skip it. But basically it says is that transition where your disorder is happening in the matrix. We'll come back to this when we do order disorder. Okay. Okay. Now effect of pressure and temperature on phase transitions. Again, there's nothing to memorize in this thing. You only have to be open to what will happen. With increase in temperature, as you increase the temperature of material, what will happen? It will expand. So very obvious is that suppose a material is undergoing phase transition and it has a low temperature phase and it has a high temperature phase. Okay. The high temperature phases are always more open structures. And because they expand and they want to become more symmetric, the atoms or the ions, they have lower coordination number. Okay. High temperature phases are more disordered because a lot of energy is there. So if there is a possibility that a crystalline form of the material uh, will undergo phase transition and there could be some order disorder, then the high temperature phase will always be more disordered. Okay. Then high temperature phases are more symmetric. They want to expand, and now because they are expanding, they would want to arrange in a very systematic manner. When I go to order disorder, I'll make that clear again. but you have to be very, very clear about this thing once I teach you that ordering and symmetry are different things. People tend to confuse between this. Disordered means lower symmetric. No, you can have a disordered material, and in most of the cases, the higher symmetric material is more disordered. Okay. So thumb rules: with increase in temperature, your high temperature phases, if the phase transition is happening, high temperature phases have more open structure, they are more disordered, they are more symmetric, and they tend to have lower coordination number. Ulta, with increase in pressure. The high pressure phases, again, you can imagine that you are applying pressure on the material. What will happen? You're bringing it close together forcibly. It will tend to have higher coordination number. They are more dense. They are more ordered, and they are less symmetric. Because you're not forcing everything to come closer. They are coming closer. They might not be able to maintain the symmetry. So in general, the high pressure phases as compared to their low pressure counterpart are less symmetric. Okay. High temperature phases more open, lower coordination, more disordered, more symmetric. High pressure phases more dense, higher coordination number, more ordered, less symmetric. Okay. Now let's take an example. We just talked about the rock salt CaCl testing. In CaCl, the coordination number of the chlorine is 8. In rock salt, it is 6. That means this transition from higher coordination to lower coordination should be brought about by increase in temperature. Or vice versa, if I apply high pressure on this structure, rock salt structure, with increase in pressure, there will be increase in its coordination number. You will go to the CaCl structure. Okay. Similarly, if you further increase the temperature of the rock salt material, I'm not talking of NaCl in particular. Please remember that what I'm talking of is CaCl type structure, NaCl type structure, and zinc sulfide type structure. So NaCl with increase in temperature will go to sphalerite or the zinc blende type of structure, and here the coordination number is 4. ZnS4 polyhedra. Zn or S occupying tetrahedral voids. Ulta on increasing the pressure, ZnS type structure goes to rock salt. On increasing further pressure, it goes to CaCl type. Okay. So these are basic guidelines that you have to remember as the effect of pressure and temperature on phase transitions. Okay, now let's come to order disorder phase transitions. Okay, now what is an ordered phase? Suppose you have mixed A and B, okay, and I'm not talking about any particular technique, any technique in particular, but you have some kind of vision, some kind of power that you are able to see where A is sitting and where B is sitting. If you are able to clearly mark that this is the position of A in my lattice, A is sitting at 0, 0, 0, and B is sitting at half, 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 that is at the body center, then that particular phase is called the ordered phase. However, if you have mixed A and B, and again, you have that power to see A and B individually. Okay. If you have the power, you will be able to anyway see it. My point is, if suppose you have a unit cell and those unit cells are joined together three-dimensionally. If in this particular unit cell, A is at the corner and B is at the body center, in the Bajuwala unit cell also A is at the corner, B is at the body center, and that repeats three-dimensionally, then that is called ordering. That is, A and B have got distinct site occupancy. However, when you are not able to distinguish, in this unit cell, A is at the center, in the Satwala, B is at the center, here again B is at the center, here again A is at the center. That means they are randomized. They are distributed in a very random way. Then you call it a disordered phase. And how will you define your one particular lattice site? That would be the composition that you have taken, which means suppose I had taken AB, then my each lattice point I would say has the occupancy of A.5, B.5. Or if I have taken 66% A and 33% B, I would say the average atom at each lattice site is A to B. Okay, so this is how it happens. Okay, in very crude way, this is your disordered phase and this is your ordered phase. Okay, now the low temperature phase is generally, if see, order disorder will not happen in all the materials. Let us first remember this. But if in any material there is a probability of order disorder phase transition happening at all, then low temperature phase is the order phase. Why? Because as you increase the temperature, that gives them more energy. Now they have, they want to be in that ordered state, but now they have enough energy, so they'll play out. So that will cause randomness. Increasing the temperature will cause randomness, and you will get a disordered phase. So if in a material an order disorder phase transition is possible, your low temperature phase is the ordered phase and your high temperature phase is the disordered phase. Okay. As temperature decreases, already A and B had some kind of specific preferences. That is why they occurred in an ordered fashion at all. Na? As I said, all the materials do not show ordering. So there are two distinguished sublattices, and you are able to distinctly say they will go at lower temperature, they will go and set whatever is comfortable to them, whichever is the lowest energy configuration. And given that ordering happens in them, for them the lowest energy configuration would be the ordered lattice. So low temperature phases are ordered and less symmetric. High temperature phases are disordered and more symmetric. So what is a superstructure? Now this is one term which you'll come across probably, in ordering, disordering or some other way. Superstructure is long range ordered structure generated after ordering of A and B. Why do I call it a superstructure? Okay, now let me just make it clear so that, later slides are also clear to you. You see this disorder structure and listen to me very carefully now. This is a disorder structure, okay? Suppose each square is an atom. I have blue atoms and I have green atoms. Now, unfortunately, your X-ray diffraction, X-ray, the wavelength of X-ray is bigger, okay? So if it is going through this, it is blind. If this, or it is blind to whether, suppose I have a bed sheet and there I have random colored squares, okay? To me, it seems randomized. Then the X-ray will see whatever is the possible 3D periodicity happening there. Okay. And that would be not on these level because it is randomized. Okay. I think I should explain it to you in some other way. Okay, let me just go to this. Maybe we go to next slide and then we see. Let us see some example and then probably it will make it more clear. Okay. For example, this cobalt platinum. Okay. Cobalt platinum has the tendency to exist in an ordered phase as well as in the disordered phase. Now, in disordered phase, this is the disordered lattice of cobalt platinum is FCC, that is phase-centered lattice. And the ordered is you have platinum here and you have cobalt here. Okay. So what is happening here is they are so much randomized that X-ray is not able to distinguish which one is cobalt and which one is platinum. X-ray is lost in that. So what it shows you, okay, this particular site, it has characteristic of an atom which is average of cobalt and platinum. This is what X-ray will tell you. And because now it is not able to distinguish between this particular lattice site and this particular lattice site, what it will show you is the unit cell is a cube which has got lattice sites occupied at the corners and face centers. So X-rays will give you that you have an FCC lattice or FCC unit cell. However, when you have ordering here, okay, now X-rays interact with the electrons. X-rays will see some difference. There is a particular ordering. Everywhere these planes are alternating. X-rays would interact here less because this particular, or platinum has more electron. X-rays would interact here more and interact here less because what they interact is with the number of electron. Platinum is higher Z. So it is able to make out the difference in electron density, and it will tell you that here, whatever is there is different from whatever is there. So what it will give you a tetragonal kind of lattice where this would be elongated. Okay. So, but then as I told you that the high temperature phases or the disordered, this is a disordered phase, and the high temperature phase, this is more symmetric. Your FCC is more symmetric than the tetragonal lattice. Okay. Now coming here to copper zinc. In the ordered phase of copper zinc, what happens is zinc is specifically located at the body center and copper is located at the corners. And because this is happening three-dimensionally, so X-ray is able to make out. See, this is a different lattice, This is a primitive lattice. There is no more symmetry than or higher symmetry than this. But when they randomize, in every unit cell, in some unit cell, this is copper, in some unit cell, this is zinc, then X-ray is lost. Then X-ray says at every atom, the lattice site is occupied by an atom which has electrons, which is average of copper and zinc. And this is what I can tell you. So basically what it shows you is a body-centered lattice. I hope this is clear. So this is a primitive lattice. This is a body-centered lattice. Similarly, in Cu3A, this is the ordered phase where your copper is occupying all the corner. Copper occupying, okay. Let me just correct this thing. This is gold and this is copper. Okay, so let us count. Corner we have gold. So how many golds are there? Each gold occupies contributes 1/8. So 8 into 1/8 we have 1 gold, and 6 into half we have 3 copper. So the ordered phase has copper atoms on the face center and gold atom at the corner. But when they randomize, again, X-ray sees them as a average atom which has 3/4 of copper contribution, 1/4 like gold. So Cu3AU. Okay. And thus it sees a FCC kind of lattice. Now, that means the disordered phase, FCC, is more symmetric than primitive. Body centered, more symmetric than primitive. That means your disordered phase has got higher symmetry. And the disordered phase will occur at higher temperature. Okay. And how will you study your order disorder phase transition? What will happen is, if I give you these two materials, I arrest it at low temperature and I ask you to record the XRD. I give you, okay, sorry. I give you this material and ask you to record the XRD, and I give you this material and ask you to record the XRD. Those of you who have studied XRD, unfortunately, I cannot cover XRD. FCC has got systematic absences, and that is why number of lines that you will see in the XRD pattern of FCC would be lesser than the number of lines in the primitive lattice. So if you record the XRD, suppose you're recording it in a machine which can vary the temperature also. We have one in our lab. It's an HT XRD machine. You set the lower temperature, record XRD of this material, increase it, you record again XRD, you will observe similar pattern. When you will reach the phase transition temperature, what will happen is it will convert to this, and suddenly some of the lines in your XRD pattern will disappear. Why? Because FCC has got lesser number of lines. And that is when you will know that the phase transition has happened. What kind of phase transition is this? It is an order disorder. A primitive is getting converted to FCC. And also, yeah, there was a third point which I wanted to tell you. Okay, yeah, and the extra number of peaks that were present in the XRD pattern of these primitive lattice, na, which disappeared in the XRD pattern of FCC lattice, those are called superstructure peaks. Okay, this is an ordered structure of this, hence this is called a superstructure of this, and the extra peak that appear in the XRD pattern of this structure are called the superstructure peaks. I hope I'm clear. I'll wait for a minute and I'll ask you to ask me any question if you want on this. Amorphous system. Okay. Yes, they are very different, Amrit. Amorphous means there is no periodicity. Random and disordered means they are randomized, but they are following some kind of periodicity. For example, uh, in this material, okay, because your copper and zinc are randomized, they are looking like this, but they have a periodicity. They have a periodic structure whose unit cell is body center. Okay. In glasses or amorphous material, there is absolutely no periodicity at all. So I hope this is clear. Do you have XRD of this? Not of this material, but I'll try to get you XRD pattern of the same material which shows order and then disorder. Okay. Actually, ideally, I didn't want to venture into fluorite and pyrochlore, but if you think about it, pyrochlore is an ordered structure of fluoride. Okay. Fluoride is a randomized structure where A and B occupies your corner and face center, and oxygen and vacancies are randomized. But when you go to pyrochlore, your A and B, they alternate in all the three dimensions. And vacancy is also fixed at a particular point. So pyrochlore is an ordered structure of fluoride. And those XRD pattern I can definitely show you because I work on them. And then you'll be able to mark out what are the extra peaks happening in the pyrochlore which are not occurring in the fluoride. And those peaks are very small and they are called superstructure peaks. Okay. All right. So now conditions for ordering. When does I told you earlier that ordering doesn't happen in all the materials. Okay. For that, atoms should be dissimilar. For example, you will never find a silver gold alloy that orders. Why? See, if they are similar, their interactions would be interaction between silver would be similar to silver gold or gold. Then what is the motivation for ordering? Why should I sit in a particular lattice site when I'm friend with both silver and gold? Okay. So conditions for ordering is the atom should be dissimilar, and that dissimilarity could be size or oxidation states. Okay. And obviously more affinity between AB than AA and BB leads to ordering, because that gives a different kind of energy landscape. And sometimes the minimum energy landscape is the one where ordering is preferred. So what is the effect of ordering? Appearance of extra peaks in XRD due to lowering of symmetry, and that is called superstructure peaks. That is, of course, one way to identify. But the effect ideally is increase in ionic conductivity or electronic conductivity. Why? Because once the material order, they are in a particular, they're lying and arranged in a particular fashion. So they cause less scattering, and where they provide better pathways for conduction. So there is an increase in conductivity. Plus, when they're arranged and ordered in a particular fashion, they are more malleable and ductile, and uh, there is a better packing and higher density in the ordered materials. Okay, so these are the effect of ordering. Now, there's one particular class of phase transition that I would want to talk about, though metallurgists know this transition very well. But I am not sure how many of you have read about it. It is called Martensitic phase transition. Now, it is a very specific class of displacive phase transition. Okay. Now, these are the diffusionless process. In the phase transition, there is absolutely no diffusion of one atom to its from one side to another side. Diffusionless process by which material changes crystal structure without requiring any of the atoms to change position by more than a lattice spacing. And it happens in many metallic and non-metallic systems. Ideally, if I want to tell you is, basically, these are very, very fast phase transition. They also happen only by slight tilting, slight twisting of the bonds. And because they require simple tilting and twisting, they are very, very fast. The speed is actually in steels, and they're mostly seen. Martensite is a steel phase. We'll come to it. It occurs at 1,000 meters per second. That is the speed of the transition. So it is very difficult to stop them. You cannot stop them. Once you reach the conducive condition, they will happen. Reconstructive phase transition, you can stop because they involve breaking and formation of bonds. Okay. And I'll come back to that, Nikita. The martensitic transformation can be induced by mechanical forces, by applying shear, or by temperature changes. Okay. And the extent of transformation, then one thing about martensitic phase transition is, unlike the normal displacive and reconstructive, they do not happen at a fixed temperature. They happen over the range of temperature. That is, suppose, okay, let me tell you why the name martensitic. A steel, that is carbon into alpha iron, at its stable phase is austenite. Okay, austenite, when you cool to the room temperature, cool means you quench it. Quenching means fast cooling. When you cool it to the room temperature, you get martensite phase. Alpha iron is cubic, martensite is tetragonal. Okay, so and this one, once you cool it below a particular temperature, that austenite to martensite phase transformation will start happening, and you will have a huge body of austenite. In between, some of the phase has become, some of the part will become martensite. Here, some will become martensite. Here, some will become martensite. So, how much of that will become martensite will depend upon the temperature. And it will happen, the temperature will decide the extent of phase transformation. Very, very arbitrary thing. At this particular temperature, say 1/10 has happened. At slight temperature below this, some more would happen. So it will happen over the range of the temperature, and the extent, that would depend, that would be fixed. That would depend upon the temperature. At particular temperature, this much extent would be transformed. Okay. And because it happens over range of temperature, they're also called athermal. And diffusions are much small. They're much less than the interatomic spacing. Also, because they're only slight tilting and twisting or slight movement, the two polymorphs are very close in their symmetry. And that is why these transitions are reversible. So, wait, I'll just get back to it. They are reversible, and that is why now austenite, you cooled it, you form martensite. You heat martensite, you will get austenite. But suppose austenite to martensite started happening at a temperature T1. But when you heat it again, then martensite to austenite will happen at T2, and that T2 will be much above T1. So this lag T1 to T2 is called hysteresis. Okay, martensitic phase transition show hysteresis. So if in one direction, from heating to cooling, they are happening at T1, from on heating, from low temperature to high temperature, they will happen at a temperature T2, which would be higher than T1. And that is why this phenomena, that they show a difference in the temperature in two directions, is called hysteresis. martensitic phase transition show hysteresis. And they move in a very choreographed manner. It is, I don't know, I'm not seeing that word using, but my perception of martensitic phase transition is, I feel it is like a dominoes effect. You know what a dominoes effect is? You arrange cards over one another and one fall, the other fall, and the other fall that way. So my perception of martensitic phase transition is like a dominoes effect. So they move in almost a military transformation. One happens, it makes the other happen, and this is how it moves. Okay. So as I told you, this alpha iron with carbon, which is your steel, the stable phase is austenite, and it is an FCC structure. Austenite, when you quench to lower temperature, you get martensite, which is body center tetragonal. But the transition happens so fast that the carbon that was sitting in the interstices, no, it remains intact at its own place. Okay. So this is your austenite and this is your martensite. Okay. I took this photograph from AR West. This is what gives me the perception of dominoes. I don't know. This is all austenite. Okay. So what happens is when martensite phase occurs, as I told you, the extent, some slabs in between will form martensite. It will happen over a range of temperature. Okay. So for example, this slab has become tetragonal martensite and these are still austenite. Okay. So that is how the martensitic phase transformation proceeds. I hope it is somewhat clear to you people. I don't work on steel. For me, I work on oxides and I worked a lot on zirconia. So for me, this is an important phase transformation in the sense monoclinic zirconia to mono. I told you that monoclinic zirconia occurs in monoclinic form, and then you can substitute and make it cubic. But even if you don't disturb zirconia by substituting anything in it, and you simply heat it, room temperature zirconia is monoclinic. At 1200, it becomes tetragonal. And at 2400, this is all without any substitution, it becomes cubic by its own. So when you heat monoclinic, this is also a monoclinic to tetragonal is also a martensitic phase transition. It occurs from 1000 to 1200. I've observed it at 1125, 1150 something. Monoclinic goes to tetragonal, but if you start cooling it, the reverse will start only below 950. Now, this is called the hysteresis of the phase transition. That is shown by martensitic phase transition and not displacive in general. Okay. Okay, I'll take a minute's break and then we'll do this thermodynamic classification. This was all the classification of phase transition on the basis of how they are happening, that is mechanism. Nitika, I'm sorry, I don't know about it, but I can definitely read about it and come back to you. Okay. Is there any other question? This perlite thing, but I can definitely read about it or talk to the colleagues who work and I can get back to you. All right. So let's come to this. Okay. Now, in terms of thermodynamics, phase transitions are described as based on their order. You would have heard about it. This is a first order phase transition. This is a second order phase transition and so on. And this particular classification based on thermodynamic parameters is called Ehrenfest classification scheme. Order is basically, okay, let me start in a very simple way. If there is a phase transition happening from phase 1 to phase 2, okay, at equilibrium, delta G is 0. We know thermodynamics, when there is an equilibrium reaction, your change in free energy is 0. When delta G, suppose I'm going from phase 1 to phase 2, this has G1 and this has G2. Delta G is G2 minus G1. And when I say delta G is 0, G2 is equal, why I'm explaining, you might find it very kiddish, but it will help you understand it. Delta G0 means G2 is equal to G1, okay? And when G2 is equal to G1, the terminology we use is, we say G is continuous, okay? So remember this thing, when some quantity is 0, and at phase transition temperature, its value for two phases is equal, we say that quantity is continuous. Okay. Now, the first order phase transition, order of the transition is the order of the lowest differential of free energy that shows discontinuity. Okay. So I repeat it, at equilibrium delta G is 0. In other words, it means that your G or the free energy is continuous. Okay. If the first derivative of free energy with respect to temperature and G is given by H minus Ts. Remember that? You know that. If the first derivative of free energy with respect to temperature and pressure is discontinuous, we call it first order reaction. You'll understand it a little more. Just be with me. Free energy, the first derivative of free energy with respect to temperature, del G by del T is minus S if you differentiate with respect to temperature. And if you differentiate it with respect to pressure, you will get del G by del P, and that is V. So, first derivative of free energy with respect to temperature is entropy. First derivative of free energy with respect to pressure is volume. And I say that first order phase transition is that particular phase transition for which first derivative of free energy with respect to temperature and pressure are discontinuous, which means S is discontinuous, V is discontinuous, which means the value, if a phase transition, phase 1 is going to phase 2, S2 at phase transition is not equal to S1. V2 at phase transition temperature is not equal to V1. That means delta S and delta V have got a finite value. S2 minus S1, V2 minus V1. Those are called first order phase transition. Tell me this is clear and I'll move forward. If this is clear, then आगे वाली चीज is smooth. Okay? Great. Okay. So, this I explained to you. This implies S2 is not. Okay, one more thing. They are discontinuous, they are finite, and you also have to remember, obviously, when they are finite, then S2 is not equal to S1 and V2 is not equal to V1. Now, S is equal to H by T, and that is why H2 is also, enthalpy of the two phases is also not equal. Okay. Now, how can I determine first order phase transition? How would I know this phase transition is first order? Experimentally, I have to know, right? So, if I try to measure the volume change happening at the phase transition, and if that is a finite value, I would say it is a first order phase transition. What other property I can measure? I can measure delta S, and it is easier to measure the enthalpy changes. So we can measure by thermal technique. How do we measure the volumetric changes? I don't know whether you know about the techniques, but we can do it by high temperature XRD. I just told you about a high temperature. I mentioned it in terms of order disorder. High temperature XRD, what it does is, you put your sample in the XRD machine and program it to record XRD at every 25 degree, 50 degree or 100 degree, whatever. And you give it the start temperature and the final temperature. So it records it at fixed interval from start to end. So what happens is the expansion would be happening because normally most of the materials expand on heating, right? So you would be able to, if there is a phase transition happening, you would be able to measure the volume changes anyway because the volume is expanding. And at the phase transition, if there is a significant volume change, you can determine by HT/XRD. Dilatometry, what it does is, you take big pellet and then you put sensors on the end of the pellets, and then you heat it, and these sensors are very sensitive. When you heat it, this pellet expands, and then you are able to measure the expansion or the volume changes. Dilatometry measures what is called bulk thermal expansion. And this is actually important to the engineers. They are not bothered about what is happening in the lattice. They are bothered about what is happening to my body as a whole. So they believe in dilatometric data. We who are more interested in structure, we believe in HT/XRD data. Okay. So it is only what application you want to use, you use the suitable technique. Okay. Now, second order phase transitions are those for which there is a discontinuity in the second derivative of free energy now. And what are the second derivative of free energy? Heat capacity. Del G by, here I've not put this, I changed this slide, but I've not changed it here. So sorry about that. This is del G by del T square, del 2G by del P square, and del 2G by del T del P. Okay. So del G by del T is minus S, and minus S ka also we take one more del T, we will get heat capacity. Similarly, double derivative of free energy with respect to pressure is this, and this particular value is of interest. This is called compressibility. Okay. And this particular value is called thermal expansion. So there we were bothered about changes in enthalpy, entropy, volume. Those were discontinuous. Here we are bothered about changes in heat capacity, compressibility, thermal expansion coefficient. And I'm sure most of you would not have measured it or would have seen this instrument. These values are very, very small as compared to volume and heat changes, which means the second order phase transitions are relatively difficult to detect because these quantities are very small. Thermal expansion coefficient, I'll give you an idea. Thermal expansion coefficient of normal nuclear materials is of the order of 10 raised to the power minus 6 per degree. That is, for every degree, it will expand by 10 raised to the power minus 6 of its length. Okay. So this is how they small are. Obviously, then they are difficult to measure, right? But most of the time, this is appreciable. So second order phase transitions are studied or determined by measuring the change in heat capacity. Okay, and that is done by calorimetry. Okay, now I don't know, most of the time I have this tendency, whenever I read all this jargon, in my mind I tend to see what is the physical meaning of whatever all this. Can you see, if you just try to sit for a minute and visualize, the changes happening in the first order phase transition are the changes which are huge. The changes happening in the second order phase transition are the changes which are small, which means that most of my first order phase transition should be reconstructive, isn't it? Okay. And most of the transition associated with the second order phase transition should be displaced because they bring about smaller changes, isn't it? Okay. So if you try to go and look behind what is happening, that gives you a much better understanding of the process happening in the material. Okay, now we'll just try to see how the curves look like. And pardon me, this is a very bad graph, but I wanted to start with this so that I can make you understand. If you want to plot G versus T for a normal solid, if you don't remember your thermodynamics, I won't bug you for that. This is how it looks like. This is a little more hump over here. It is more like this. Okay. But this is in general. I just drew it just before coming to the lecture. So that is why I goofed up. This is how the GT curve look like. Now keep this in mind. Okay. Now for a first order phase transition, this is your T transition. And what did we talk about? at equilibrium when the phase transition is happening, delta G is 0, G is continuous. That means G2 should be equal to G1 at phase transition temperature. That means there should be a single G value. And that is what we see here. Okay. This is G1. This is G2. This is the transition. That is how we draw. Okay. Volume changes. This was your phase transition. And we know that volume and entropy and enthalpy are discontinuous for the first order phase transition. Isn't it? So this is your volume of phase 1. This is the phase transition temperature. And this is your volume of phase 2. So there is a huge discontinuity in the volume of two phases that are connected by this particular phase transition temperature. All right. Similarly for enthalpy. Okay. And similarly for H. Now, because here there is a discontinuity in H, the H is not equal and your Cp is H by T. So for the first order phase transition, if you want to determine the Cp at phase transition temperature, it would go to infinite at this particular temperature. Okay. And what are the reactions phase transition that correspond to first order? These are of course not associated with the solids. Polymorphous phase transition happening between two polymorphs, the reconstructed phase transitions. Okay. Now for the second order phase transition, I normally spend some time on it, but okay, I will do it. Right. Now, why did I show you that GT curve? You know that the shape of GT curve is this. Okay. Now, my second order phase transition, second order ka definition says G anyway has to be continuous. Now, H and T also have to be continuous. H and V also have to be continuous. S and V, sorry. What is S? That is del G by del T. And all of us know what is del G by del T? Slope of the GT curve. dg by dt, slope of the GT curve. Now, if in the second order phase transition, the slopes, now I know that phase transition, I have to draw two GT curve, and I have one more condition that at phase transition temperature, the slopes also should be equal. All right. This is the condition that I need to follow, which was not the case in the first order transition. The slopes could be different. The slope of this is different from the slope of this. Why? Because the slope is entropy and entropy is different. So it was fine. Here what happens is you have to draw GT curves, making sure that the slope of phase 1 as well as the slope of phase 2 are same at T is equal to Tc. How can we attain that? This way. But what does it mean? This is wrong. Why is it wrong? All the time, your phase 2 has lesser free energy. That means phase 2 is always stable. Then how would phase 1 occur at all, exist at all? So this is wrong. This could happen, but this involves distorting the GT curve of at least one polymorph. And that is, you know, a very, very kind of not a feasible thing. So this is also wrong. Which means, how can I draw the GT curve depicting second order phase transition? So you look at this. So basically, GT curve, how can we draw? We say that second order phase transition is a phase transition which starts happening, okay, at 0K or at some low temperature. It goes on happening, and at phase transition also it is happening. I mean, there is no significant change in the GT of 1 or 2. And you extrapolate it backward. So this is your GT curve of phase 2 and this is your GT curve of phase 1. Now, what does that lead to? Let me skip 2 slides and come to that, and then I'll come to other things. Look at this. Okay. Try to understand this. It's a very, very interesting and important concept. This is the GT curve of phase 1. This is the GT curve of phase 2. And this is the your first order kind of thing, if you remember. This is your first order. It happened this way. Okay? This way. Which shows in this region, phase 1 is stable. because its free energy is lower than 2. In this region, phase 2 is stable because its free energy is lower than phase 1. And that is why we observed a phase transition at Tm. Na? But what it shows is that if by any chance, this is the high temperature phase, this is a higher temperature zone. If you are able to suddenly quench it, drop it, and it goes to this temperature range, there is a possibility that you can obtain phase 2 because the GT curve has some existence. Okay, even though it would be metastable, it would have higher free energy, but there is a possibility that it could be stabilized. Similarly, if you heat this phase suddenly by laser heating or by some unconventional method, there is a possibility that you would be able to obtain phase 1 as a metastable phase here because this is the zone of stability of phase 2 in first order phase transition. However, if I go to second order phase transition, this GT curve of 2 extrapolates back to here. That means there is a possibility that I can supercool 2 and obtain as a metastable phase, but there is absolutely no possibility that I can superheat 1 and obtain it because there is no existence of GT curve of 1 beyond TC. It has converted to GT curve of 2. Okay, which means first order phase the two polymorphs related by first order phase transition, there is a possibility of them being obtained in the metastable phase, but you cannot do this to the polymorphs that are related to second order phase transition. Because second order phase transition, when that happens, it means end of 1 converted to 2. Okay, it has something has happened which has changed 1 into 2, and now 1 ka identity doesn't exist at all. Okay, I hope this is clear. Think about it. We can also talk about it again in the next class towards the end. Okay, now because we are already over the time, ending the lecture. Second order phase transition, this is how the GT looks like. We just discussed volume and entropy and enthalpy are continuous for second order phase transition. So you see this kind of behavior. However, CP value for the second order phase transition for phase 1 and 2 are distinct. So you observe a distinct change. Okay. Okay, all right. So concept of metastable phase. Metastable phases, all of us know that stable phases, they occupy the free energy minima, the absolute minima. Okay. However, if in the energy diagram, there is some minima which might not be the absolute minima, but it is still some minima, the local minima that we call it, then that phase is called the metastable phase. And you can obtain the metastable phase by thermodynamic condition. You will never be able to obtain it because it has higher energy than the stable phase. However, if you carry out your reaction, which we'll talk about in the next class, there are some synthetic procedure by which you can carry out the reaction wherein, the reaction happens suddenly. The thermodynamics do not get the chance to cover up. That is called kinetic control of reaction. So kinetic control of reaction can give you metastable phase. And sometimes what happens is metastable phase 1, once it forms, the minima is enough that it cannot go to this side or this side. And once it is formed, it can remain stable. For example, diamond is the metastable phase of carbon at room temperature. Otherwise, the stable phase of carbon at room temperature is graphite. If diamond, even though it is metastable, if it was not retained once being formed, all of us would have lost our jewelry, that would have been a big loss. So metastable phases, if they have enough energy minima, even though they are not the absolute minima is the stable phase, once they are formed, unless perturbed, they can be made to stay in that particular energy state. Okay, this we have already talked about. For a second order phase transformation, the free energy is a single continuous curve and the concept of metastable state does not exist for that. Okay, this again a comparison G versus T for first order, second order, H a sharp jump first order, continuous for second order. CP goes to infinity for first order. There's a finite value for second order. And of course, we have not talked about order, so I'll not confuse you further. So what did we learn today? We learned what are phase transition, what are the classification. Based on mechanism, we can call them reconstructive, displacive, and martensitic, which is a special class of displacive, and thermodynamic classification and effect of pressure and temperature on phase transition. Okay. So sorry, that was a little longer class and involved a little more concepts, but I hope you could get a feel of what I was trying to say. If that is also the case, I would be very happy with it. And I would be really open to taking up your questions, even after my lectures are over. Okay. So thank you so much and good day, all of you. Okay. RO, how to calculate coefficient of thermal expansion. You record XRD at let's say 100 degree, determine the lattice parameter from XRD pattern. Like usually हम लोग कैसे निकालते हैं XRD से? Record XRD at 200. Again record the lattice parameter. Thermal expansion coefficient is lattice parameter at T2 minus lattice parameter at T1 upon lattice parameter at T1 into T. That is your thermal expansion coefficient. Is that okay? I hope RO is still around. Okay. Okay. So thank you very much. Good evening and good day to all of you.